So Jolene, how's the video, the recordings? Did you find them helpful in catching up?
Yeah, absolutely. Yeah, they were really good. I usually watch them a little faster than normal speed.
Yeah.
But no, it's been great. It's kind of weird. I feel like I know everyone just because I've been watching the videos.
Yeah.
No, it's awesome to be able, just if you can't make a session, to be able to catch up. That's really great.
Well, I'm really glad to hear that. But that's very true. There are certain YouTube channels that I watch, and after a while, you do get that sense that you're very familiar with these people. They have no idea that you exist, obviously. Okay, so the agenda for today, we'll just continue where we were in TAOCP. And this is the section still dealing with sort of allocating memory for lists and different schemes. But here, the focus of this section is a pretty important algorithm for topological sorting. And so it's nice to be able to finally, look at a serious algorithm, because up to this point we've looked at some algorithms for memory allocation. There was one for finding the maximum. I mean, those are like relatively simple and straightforward problems, but this topological sorting problem is often used in applications. So that's really nice. It's relatively simple, so it's not that complicated, but I think it does require a little bit of attention. And so we'll be able to use some of the new allocation schemes for linked lists for this algorithm and the program. And since there is quite a bit of material, even in just this one section, I felt like I'd break out the program piece of it and sort of make it kind of optional in a sense. If any of you folks want to stick around, that would be really great, because obviously, it just makes it more enjoyable to do this in a group and then for the recording as well. But my primary purpose was to at least cover the material, and like Jolene is mentioning, and other people have also given me this feedback that they are using the videos and the recordings. So at least we have the recording, and then we're not compelled to fit everything into sort of a live session, and we can keep moving along. So that'll be like at the end when we've covered the algorithm, we've done maybe a few exercises, and again, if that's like around 4 p.m. and you have other things to do, that's perfectly fine. I'll just continue with the recording. And okay, so just our process for reading. I think everyone's attended at least once or seen the recording, so you know how it goes. And we will just go ahead and start with the top of section 223, linked allocation. You have about 5 minutes till about 2:15. Okay, so would someone summarize the trade-offs between a linking allocation versus a sequential allocation?
So what I get is a lot of echo. So in the sequential allocation, you basically put each element after the other, and since they are all sequential, one after the other, then by just having you can reference them by index, right? So you have a number multiplied by the size of the word, then you know exactly where the element is. Where on the other hand, if you want to keep maintaining the sequential allocation can be time consuming, right? Like if you want to insert an element in the middle of a list, you have to move the whole thing to one side. And in general, to keep track of the memories, it can be time consuming when there is a lot of stuff in it. Whereas in the linked list, you can put things wherever you want as long as you have the reference. So the only real drawback seems to be if you want the nth element of a linked list, in which case you have to just traverse the whole thing. But other than that, most things can be, if you know where to look, it's almost always constant time. Right? You have the address at hand. And usually you want just to, I mean, in our experience, right, you always want either the first element or the last element of any given list in many occasions for a stack or queues.
Yeah, so those are really great points that you brought up. So let me see if I understood all of them. So one disadvantage you said was traversal, right? If we want to access something in the middle of a list, then we have to go through all of the nodes before that, or in some order from one end of the list. But what did you mean by, you said that something was constant time access? What did you mean by that?
I meant if you know the address, yeah, you're right. So you usually will keep a reference to the first element of the linked list, and you could, if you care, a reference to the first element. Therefore, getting the first element is always just loaded from memory. You don't need to traverse it if there is no extra steps. So what I understand is as long as you don't need the nth element of a list, most of the time you just want the first or the last, depending on how you see it, for a stack. So what I meant, if you have the memory address, obviously you just get the element, and in many occasions that's all you have. That's what you have.
Okay, so yeah, so for certain data structures like a stack or a queue, you won't be accessing something in the middle. You'll only be inserting or deleting from one end, or possibly both ends if it's a deck. So then, but you could do the same thing with sequential allocation as well. So then what's the disadvantage of sequential allocation? Because with linked lists, you are definitely using much more memory, right? Because now you have to maintain a link with each one of those nodes. And depending on how big your node is, that could be anywhere from doubling the size of the node to, maybe a smaller percentage. Yeah.
But you still need the extra memory when you're doing sequential allocation, right? Even if you do the fancy algorithm to give the 10% of the free memory and all those stuff. So you still need the extra memory anyway with sequential allocation. Maybe not as much, but you still need extra. And then as it grows, you will need more time just to keep track of it all, right? I don't remember what's the operation, Yeah, when you need, yeah, exactly. When you are about to hit overflow and you do need to do all these like fancy algorithms of moving things a little bit to reorganize the memory to make more space, it will take longer and longer and longer as you have longer sequences, longer lists. Whereas with the linked list, it's always the same. As long as you have memory, you just keep traversing the thing. It doesn't matter, right? You don't need extra memory. You need the extra memory of the links only.
Okay, any other opinions or comments?
Well, for a linked list, you do need extra memory because a linked list is link info, link info, link info, and a sequential link is just info, 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 info. So you, for every node, you need those extra bytes to store the link. And I suppose you could argue that the linked list is more dense because there's there's no free space like there is in the sequentially allocated, but you still have that pool. That works out to be the same, I think.
Right.
Yeah, you're right.
Yeah.
What I meant was in the sense, as you have more elements in your sequential list, once you are about to hit overflow, that you need to reorganize your memory to make more space. You remember that sometimes you have like these overlaps, and then you have to move things around. It gets slower, right? As you have more elements.
Yeah. Okay, so you're talking about the later example where we kept multiple sequential lists, and we could if one of them overflowed their bounds, we could move the other ones around to make room. Yeah, that's a good one.
Okay, very nice. All right, so let's move on. That was just sort of a general, more abstract level description and explanation of the comparison between a linked list and sequential allocation. We'll get more and more into the details now. So we'll just continue pages 256 to 258, another 5 minutes. Okay, so this introduces the issue of overflow with linked allocation. So could someone explain what the issues are and what solution has been proposed?
It's the same issues that we had with sequential allocation. Except now we have the pool, which also can underflow or overflow, and then there's also the problem of initializing the pool, which he gives us two ways.
What did you understand about the juxtaposition of some area that's being used for sequential allocation and another area that's being used for as the pool?
Well, I think he said somewhere that programs might have both kinds of lists, both a sequentially allocated and a linked list, linked allocation. They might need both. So you don't want, if you're going to have to divide the memory up and in advance, you don't want to give it all to the linked list by using that first algorithm to make the available pool, put it essentially. The first algorithm is to take the available memory and put it all into a giant linked list. I mean giant in terms of however many bytes or however many words you allocate to it. And if you do that, then you have nothing left over for the sequential list. So the second algorithm solves that in a way, because you kind of have this either max pool or min pool well, max pool that lets your sequential list grow up to that size, and then your once you take beyond that, then you're running out of memory. What would that be? That wouldn't be either. That would be a what would that be? I guess that would be a underflow on the pool.
Yeah. So the way I'm trying to visualize that is, probably this makes no sense, but just by the implication of that algorithm, what I see is you will have like two sections, possibly, in your whole memory. One is for linked stuff, and the other one for sequential lists, all of them, right? So you say, and sigmin would mean that this is the address when it's all sequential, and before that everything is linked. So the algorithm starts with no available memory at all, and pool max presumably is like the start of the memory of the first address, and then it basically will creating available space by just using it, as long as the first try that tries to get an available chunk of memory, we won't have it. There won't be anything available. So it's going to say, therefore take the space that is at pool max current, which is pool max will be the beginning of memory of the chunk of memory that we want to use. And that's what we're going to, that will be available. Avail still will be null, but now X will have, we'll have an element, and the next pool max will be the next step, right? So the size of the word that X is, at the end of that size, that's when the next pool max is. And it can grow up to sigmin, and if you delete an element from your linked list, that element actually will now go to avail instead of to the nothingness. So you could, I guess that means that you could be deleting stuff from any part of your list, and now that space will be right. Remember, in the available linked list. So you won't need to keep using the pull max. You wouldn't need to keep increasing where you are putting stuff. If you delete things in the middle of the list, you can now reuse that free space because it's an avail. That's the whole point of having avail, right? That's what I understood from that.
Yeah, that's true. But I think that just in terms of reclaiming a deleted node, that's in the original scheme as well, because that's sort of the stack.
Absolutely, no. It says at the end the operation of removing to available is unchanged. What I realized as I was speaking, is that there is two ways to find free space. One is get it from the avail linked list, and the other one is going to pull max, right? So I realized that the way to get stuff into available is to deleting things from the first list. There's no other way because it begins empty. So I realized that's the mechanism to know that you can where you can find more free space. It will be where you deleted stuff too. So
anyone else have any comments or explanation, especially about the pool max and sec min boundary, I guess?
So what I found kind of strange was that this idea that, the big advantage that linked lists have over sequential memory is that they're dynamic and, we don't have to know in advance how much memory we need. But then suddenly here, like in the first part, he's saying, well, actually, we do need to know how much we need because we need to put all of these nodes on this available stack. So I feel like the pool max part is, like what Miguel was saying, it's just kind of like, how do we get kind of the best of both worlds without having to declare all of this stuff up front, but rather just take it as we need it. Otherwise, it's not much better than just having like two sequential allocations.
Yeah, I think in the linked list. Yeah, go ahead, Michael.
No, I agree with that 100%. The algorithm with this with what is it, pull max and seek min. It's just using a sequential allocation of memory for a linked list, where you could have just used that same block of memory for a sequential list and gotten all the advantages of a sequential list without having to have all those extra pointers. But I think the thing is that what he doesn't make very clear is that when you try to ask for another node from memory and your pool max is at seek min, so you're out of memory on that particular, the pool is out of memory. What a real system would do is it would allocate another page of memory from the operating system and map the memory that way, so that you have another block that can grow from that can grow from what the current value of avail is to the new seek min, I guess. I guess the thing I'm trying to say is that when you have exhausted the pool, it doesn't say that you're out of luck at that point. You may be able to do other things, which I think he talks about later on in the chapters on garbage collection. But in addition to garbage collection, there may be memory management that you can do.
Right. I think that that's what he's saying when he says that the overflow alarm needs to be sounded if pool max does happen to be
overflow alarm needs to be sounded, but that doesn't mean your program crashes.
Right. You could have a handler for that. Right. Okay.
That's a good way of putting it.
Yeah. Great. Yeah. So we're just continuing on page 258. through page 259. And this has a little bit of code in there, and there's the MMIX Supplement equivalent that you may want to consult. And in fact, there was a reference a little bit in the MMIX Supplement, even on the previous pages, that is useful to know. But definitely here, you will need to look at the MMIX version of the code. But the general text is obviously from the main text. So 7 minutes to about 2:47. Okay, so who can explain the two pieces of code? I guess we can just do one insertion, the insertion case really well, and then deletion I think is very similar. And if there's anything else to explain.
Where's Arthur when you need him?
He's a good volunteer. He's an enthusiastic volunteer.
I can give it a go.
Okay, great.
I got it. All right. So it took me a while, but this is the third time I read this. Not today, like since last week. To understand the whole link and info thing. So let me start with that. So it seems, so it's obvious. So for me, it was weird, the whole using the offset. So basically what I understand is, let's go through the code itself. So first it says that link is 0 and info is 8. I understood eventually that means that when this is for we want to do like a load octa from unsigned, and you do then the dollar set from the it was a load octa from unsigned was X, Y, and Z, right? So the set was the offset, and I finally saw why that was important. So you're using the combination of the link and P. So P has the actual address, the starting address, and the info or link will be the offset. So you will load just that octa rather than the octa that you wanted, either the link or the actual data. So that's the link and info. Then it sets the address in the magic register available to P. So P now has that address that wasn't available, right? So it's actually just an address. So the next instruction, I don't quite understand it. That is branch if 0, right? So if overflow, what does that mean? So if P is 0, then do whatever is overflow. I don't understand what that's supposed to mean.
Yeah, so that's saying exactly what you said, that if P is 0, then go to overflow. So overflow is probably some subroutine for handling overflow, and that's just left implicit. So that's what we would call the overflow handler.
Okay, sounds like magic. I mean, the whole point of using machine language was to not have magic, right? So well, we do have magic. So if that's fine, it takes, so that with the offset, right, of link means this is the first octa of the double word thing, the 2 octabytes. The first of the 2 octabytes loads the data of that address. So it treats it as an address and loads that data into available. Wait, what? Yes, the address into available. All right, so the link of P. So available, what we got from available was the 2 octas. And now we are saying, okay, now the new available is the link of the available that we just got. Right? So it's making that the next available is the available that was after the one we just got. So it's the next address that is whatever it is that is available. And then now we know what is the memory address that is available. Then we put Y, the data of Y in that. The Y is an octa, obviously. So we now store that octa, that number, into the octa info, the value, with the offset for info. So now we have info there, and we load T, which is the head of the essentially the head of the list, and wait, what? So we store T in the link of P. All right. and then T is the new head, and P is the address to the new element. I think I jumped over. This is sometimes it was hard to think in terms of when is an address or when is actual data. So P is always referring to address, and the only time we are talking about data, so it's the address where the whole two words are, right? Is that what we are saying? Most of the time.
Anyone want to expand on that or answer Miguel's questions? Yeah, so I think that's what it is. Where the node that he's describing has 2 octabytes, and the first octabyte at offset 0, obviously, is the link, and the second octabyte is the data, or what is being called the info field. And so the offset of info is 8 bytes. And you'll see this again and again throughout the MMIX code is, first of all, the uppercase naming for like constants and field offsets, generally like small numbers. And then the lowercase naming for registers that are somehow using or representing those uppercase values, but transformed in a different way. So often that will mean is that some address has been added to that offset to give you the final address of the memory location. And yeah, so this is right. You've got the available list, and we are assuming that the avail register has the address of the next available node. So we get that next address, we give it to P, which is going to be our new node. So P now gets the new available node. So now we have to use the link in P, because P came from the available list, so its link points to the next available node. And so that next available node needs to become the current available node. So that's what Miguel was talking about. And then finally, in the last 3 or 4 instructions, we're setting the data in the new node, and we have to write that to memory. And so after the piece of code, he says this takes 7 new and 5 mu. And if you remember in fascicle 1, I don't think we covered this in much detail, but it's sort of the timing information or the cost information of MMIX instructions. And the new, which is the Greek letter that looks like a V, that's the number of cycles that it takes for each instruction. And there are 7 instructions. So that means it takes 7 cycles or 7. And he calls the new, I think he calls that oops, like operations, something for ops, right? So he calls it oops, and the mu, he calls that mems, like memory accesses. So there's 5 memory accesses, and you can verify that that is indeed the case. So wherever we need to load something from memory or we need to write something from memory, that's going to be a memory access. Okay, and deletion is very similar. So if you understand insertion, then the code, I think, translates pretty easily. All right. We have a couple of minutes. I think we can at least read the next portion. And so that's page 260, just continuing. And we're dealing with the case where where we have some boundary conditions. You have about 5 minutes. Okay, it's just a little after 3, so let's just take a 10-minute break now, and we will come back at 3:13, and we'll start with the discussion of what we just read. See you. Okay, we're back. And we just looked at the cases when the list would be empty, these sort of boundary condition cases, and they are slightly tricky. And Knut does point out that what he's explaining is just sort of based on the operations that he had described earlier. So you don't have to do it this way. This is just one way of dealing with the empty list situation. So who can explain the couple of operations for insertion and deletion? Inserting into an empty queue. What do you need to be careful about?
I can have a go. So if in this kind of normal algorithm that he gives to us, we don't update the F pointer because when we insert, because normally we want the F pointer to stay at the other end of the queue that we're going to read from. So we need to add some kind of conditions, or we need to add some extra stuff to the algorithm to make it work properly in the case that we're adding to an empty queue. So the thing that he suggests that we add is we set R to be the location of F when the queue is empty, and we assume that F will be equivalent to the link that is in R. And if we do that, then this algorithm works for the empty case.
Yeah, that sounds good to me. Anyone else?
A cool implication seems to be that there is only one empty seek.
There's only one empty what?
Per R. So if R happen to be global, no, sorry. That there cannot be two empty seek if they have the same R, essentially. No, two empty seek, sorry, queues. No, there cannot be two empty queues if they have the same R. Sort of like R indexes the whole queue.
Every queue would need its own F and R, if that's what you're wondering.
Yeah, not very important.
Yeah, definitely. Here, the assumption is you're dealing with one queue and its F and its R. Okay, great. And then for the deletion case, if you're deleting and it's going to result in an empty queue, well, I guess we have both cases. You try to delete from an empty queue, and then the second case is you delete from a queue and then the queue becomes empty.
Yeah, it just makes, so it's basically making sure that you will have R to be the location of F, right? So you're making sure of that by adding that to the deletion algorithm.
Yeah, I like a scheme that it's sort of, it's relatively simple. You just have to make sure that this F then, is the null pointer in that sense, and then you treat it correctly. And then you can just use the same steps. So you don't need to have like a very special case for insertions and deletions and handle the empty case separately, in some sense. Okay. Anything else? Any other comments or questions about this portion? All right, so let's move on to topological sorting. The next couple of pages describe the problem, and there's a bit of math in there. I don't think it's that complicated, but you know, we can go over it later after the reading, but I think the general problem is pretty easy to understand. So we'll spend about 5 minutes on this. Okay, so who wants to go over the problem and then the high-level solution that Knut mentions towards the end of the reading?
So he's talking about the partial order, right? Where no two elements can be at the same time. It's not. So to understand, I actually didn't understand partial order to be this, but possibly Knut is better than me.
Can you maybe just explain the diagrams then? The two diagrams, there's the partial ordering diagram and then the ordering in figure 7.
Good idea. So the figure 6 has a relationship diagram when it's saying essentially that 1 comes before 3, and then after 3 comes 7, and after 7 can have 4 or 5 immediately after, right? So it's essentially a hierarchy of what comes first, right? And then a topological ordering, which is what we're talking about here, is a linear ordering where the relationships of the partial ordering are preserved. That's all what we're talking about here. And then we know, for example, that 1 is before everything, and 6 is after everything else.
Okay, so how do we do that? The very last paragraph that we read, what's that high-level solution?
So it's basically deleting stuff from the partial order. Like you first find you need to have a link to the element. You need to start with the element that is not linked by anything, and you start removing it from your diagram until you have nothing there. And when the result of that traverse is the topological sort. I'll be right back.
Okay, yeah, I think that's a pretty fair description. Can you apply it to figure 6? How would that proceed on figure 6? If somebody else wants to do it, because Miguel has already explained quite a bit. Applying that technique of finding the object or item that doesn't have a predecessor and then removing it from the set.
Yeah, there's not necessarily just one item that has no predecessor. Like in the diagram on figure 6, it's a little hard to find, but 9 has only outgoing arrows and no incoming arrows. That would mean that 9 could start the list, or 1.
Okay, let's say we start with 9 because the one solution he's shown that. Let's do it with 9. So we start with 9, then
what you can do to find a next element is you can remove the 9 from that graph and all of the arrows, and now you look for another one that has no incoming arrows. And now you have 3 choices. 1 can still come next because it still has no outgoing. It only has an outgoing arrow, no incoming. And since you've removed 9 and its 2 arrows, 2 and 5 are also good candidates for the next element. So you can pick any one of those.
Go ahead.
There's not just one answer.
Go ahead and just pick something and go on.
All right, so you could pick 2 and then 5. And then you would remove the bottom 3 nodes of that. I mean, I'm doing 2 steps at once there, but you would remove 2 first, and you have to picture for yourself now that 9 and its 2 arrows are removed, and 2 and its arrow is removed. So you have 5. 5 cannot be removed because 5 has an incoming arrow. It's just pointing down. So after you've removed 2 and 9, the only one that can come next is number 1, because everything else has an incoming arrow. So then you can put 1 and then 3. Those two you can obviously do. And at that point, there's no arrow coming into 7 because we've removed 3. So 7 would be the next one. And after you've removed 7, then the next one could be either 4 or 5. So what you're doing is you're putting elements into the sorted list, and to find the next element to put into that sorted list, you're just finding an element from this graph that has no incoming nodes, no incoming arrows. And so after you put the element into the list, you remove that node from, he calls that diagram on figure 6, he calls it S. And you could remove, you remove what you put into the sorted list, and you remove those arrows. And now you find another one that has no incoming arrows. Eventually you remove everything from the list, and everything is in the sorted. You remove everything from the graph, and everything is in the list.
Okay, and then you have a way to proceed in a linear manner, preserving the dependencies.
Right. It isn't the case in that list that you can say, I guess, let's see, I think the list is shown, yeah. It isn't the case in that list. Like when you get to that list, you look at 4 and 9. We don't know whether 4 comes before 9 or 9 comes before 4. That isn't guaranteed, but we know that everything that comes after 4 either has that relation and it's in the right order, or we can't even compare them. So that's the thing about partial ordering. Partial ordering is a lot like less than and greater than. That's why the symbol looks the same, but there are also items that we cannot compare. We don't know.
Exactly, and that would be the difference between a partial order and a total order. So a total order would be a partial order that allows you to compare any two elements.
Right.
Okay.
And there's also items like 1 and 7. If you look at 1 and 7 on the list, you can see that 7 does compare to 1 because there's a path between 1 and 7. But if you look on the list, there isn't an arrow from 1 to 7. If you look at the figure 6, there isn't an arrow from 1 to 7. We never got that as input that 7 comes after 1. But we have that transitive property. We know that 3 comes after 1 and 7 comes after 3, and therefore 7 comes after 1.
Right. Okay, so, well, maybe you've seen topological sorting before. Maybe you've read the section in advance. In any case, we're going to read the algorithm, but just sort of off the top of your head, what difficulties do you see with, actually now coming up with an algorithm? So I wanted to somehow discuss this step that is often like very problematic. I find it very problematic for myself, which is going from a high level understanding of a solution but then coming up with the algorithm. And then there's, of course, the final step of actually writing the code. But what are the challenges here? Like, we understand how to do this. How do we come up with what would be the things we really need to figure out for an algorithm? Just start with anything. Like, what would you need to be very clear about?
One thing is that, like Michael was saying, I'm not sure if there is an easy way to figure out which node is not preceded by another one. It sounds like you would have to go over the whole graph in order to find one.
Okay, so that's fine. I mean, maybe it's not a great way to do it, but how would you do that? I mean, the question is really for an algorithm, not necessarily in the beginning to come up with a very efficient way or optimized way of doing it, but just any way to do it. Like, can we, when we actually solve this problem in an algorithmic way, we have to, be very, very precise and clear. So what would that involve? Michael, did you want to say something?
Well, when you're talking about problems, are you talking about things like boundary conditions and error conditions, or are you talking about things like Jolene said, which are problems that mean that the algorithm is difficult? Like I agree with her, the way that that's expressed, it starts off with looking through that diagram and finding something that has no incoming nodes. Well, the only way you can do that is to look at every other node and see if it points at the node that you're about to delete. And if you go, or about to move to the, let's say we're moving the node from the graph to the list. So
yeah, it's coming out of that. But
if you were working in an artificial intelligence problem and you had a graph with millions of nodes, that could take a long time. But that's not really a problem with the algorithm, like you say.
I'm just saying, coming up with the algorithm in the first place. We have a solution. We have a description of the solution. And Michael, you described it really well using pictures and sort of hand wavy stuff. But now, how do we, turn this into a step-by-step thing with precise meanings? And part of it is the representation that you're implying, that, that is going to affect how you go ahead and proceed. So, obviously we're going to read it and you've probably even read it, but what is that representation?
So I imagine that we need to keep track, the same way we keep track of F and R in a queue, you will need to keep track of that as the list grows. So I can see that in figure 6 we have a regular linked list, right? It just happened that, for example, 4 and 8 both link to 6, right? So that is in the very same code that we saw for insertion can be used here. The only thing would be that we will need to keep track. So the algorithm no, we have T already, right? So T is the element that links things, but nothing links to it, right? So basically, we already know T. So T is the one that can be deleted for sure, and we would be able. I mean, basically, we'll be traversing that from T. And the only missing, like the only gap that I can see here is that at some point we need to make the decision of, as you said, as Michael said, that for example, in the case of 4 and 8, they both link to 6. Now, the forking part is the part that can be like weird. So you started with 1 that has a link to 3. Then you get to 7. The 7 has 2 links. What? That makes sense. Wait, how can 7 have 2 links? So I guess that the structure has to be richer.
Yeah, so that's the only thing I meant to do at this point, was really just to give you an opportunity to think about what the issues could be, because when you read this stuff, it often will seem very natural, like, oh, wow, this is, yeah, I mean, I understand. But there's very real barriers to having an understanding of a solution and then coming up with the algorithm in terms of how's the input going to be represented. When the input is processed, what is the other representation that will allow us to work with the solution, or implement the solution in a reasonable way? And then what's the output going to be? What are the transformations that are going to apply to the representation that we generated from the input that will lead us to the output. So let's just go ahead and read the implementation or the algorithm piece on starting on page 263, and spend about 5 minutes on this. It is still a diagrammatic explanation, and then the algorithm will follow after the discussion. Okay, so here we go. What is this diagram or set of diagrams saying? Now we have a lot more details.
So I'm still reading.
Michael, you want to give it a shot?
Well, it's the arrows. Actually, that the way I look at it is it's the arrows. The number on the top. We're talking about figure 8, right?
We are talking about everything on page 264 from the beginning of the, where the input is described and then the actual.
Okay.
Yeah.
Well, the meat of it is figure 8. So I'm talking about figure 8 here. So
okay.
What I look at, it took me a couple of times to go through this to get it because figure 8 is the way I think of it. It is it's the arrows, and which way is it? So the number on the top is the node that the arrow points to, 1 through 9, and the list is the list of all the nodes that point to that particular node. So if you read from the left to right, it says 3 points to node 1 and 8 points to node 2. And where it gets interesting and where I got confused is on the 7, because 5 doesn't have any relation to 4, but the relation is, 5 doesn't have any direct relation to 4. If you look at the diagram, 5 and 4 are not connected, but they are connected because they're both successors of 7. So they're in the list for 7 because these. So what you've got here is the nodes and all of their immediate successors.
So this essentially is an adjacency list of a graph, right? Where so I have to say you. So essentially saying, it's a group. It doesn't mean that that's the sort. It's just that these happen to be the adjacents to 7.
Yeah. The input is the adjacency list. So the input at the top of page 264 is the adjacency list. This is the adjacency list, but it's grouped in a way.
No, what I'm saying is, what I finally got is that list 4 and 5, they don't mean, as you said, they don't mean to be
right.
To know if 4 and 5, if 5 goes after 4, you have to now go to 4 and see who is, if that's true, essentially. Right?
Right. It doesn't say anything about whether 5 comes after 4. It just says that 5 and 4 are immediate successors of 7.
Well,
there could have been an error between 4 and 5.
4 is after 7 and 5 is after 7.
That's all it means.
There is nothing between 4 and 5, essentially.
Well, it doesn't mean that there's nothing between 4 and 5. There could have been. That won't be shown here.
So it would have to be a cycle then.
That wouldn't be a cycle. If there was an arrow between 4 and 5, there's still no cycle.
So if you go to 4 and then there is 5, so it means that 7 to 4. Yeah, you're right. There's no cycle, but I'm trying to picture it anyway.
Right.
So
right. There could have been. There isn't, but there could have been a link between 4 and 5. What there could not be is a link between 5 and 7, from 5 to 7, or from
yeah. So basically, it could be an arrow.
Right.
4 to 5 or 5 to 4.
Right.
It doesn't matter.
Right. Right.
Fine. Yeah.
And if that had appeared in the input, he's not checking for that. So I don't know what would happen. It would probably crash later on.
What would crash? I think it would be just in the adjacency list of 4. So 4 would have 6 and 5.
6 and 5. What?
So if, for example, there was a link, supposed to be a link going to 4 from 4 to 5, in these box things, there will be a 5 and 5 will be in two lists, in 7s and 4s. Right?
That's fine.
Yeah.
But
what will crash?
What I'm saying is that if that input up the top line there had also had, if that had also had 5 is a predecessor of 7, that would not be possible to topologically sort because you have a cycle. But in this diagram, you would see 5, you would see the 7 underneath 5.
Okay, so top of page 264, we have the pairs that describe the relations.
Which are the arrows.
Which are the arrows, right? And so we have 9, and then there's that symbol, and then a 2. So this means that 9 is a predecessor of 2, or in other words, 2 is a successor of 9. Is that accurate?
That's accurate.
Okay, and so on for each of those pairs. Michael, could you maybe run us through a couple of, maybe 2 or 3 of these pairs and explain how we ended up on figure 8? Like from the very beginning, let's say we've got that 9 pair
so
2.
After you process 9, so look at the first element. And what you're going to do there is, since 2 is a successor of 9, you're going to put 2 in 9's list. So that 2, and the counts all start out as 0. So all of the counts, before you've processed anything, all these counts are 0. I glossed over that. But you start off with 0. And then after you look at that first element, you put 9 in that list. You put 2 in the list that has the heading 9. And you also go to the 2 and increase its count to 1, because what that count is that's the number of times that element appears as a direct successor. And that's important because just looking at that first element, remember that when we're going to build our list, the first thing we're going to do is we're going to look for elements that have no direct predecessor. So by putting that 1 into the count column for 2, we know that 2 cannot be the first element of our list. So after we've processed that first element, that list on the very end has just the element 2, and the list in 2 is still an empty list, but that count field is now set to 1. And you repeat with 3 and 7, and that does, and so on. I mean, I don't know where it gets interesting. It gets interesting when you insert 5 from 9, maybe, I don't know.
Yeah, that's right. So
3 and 7 is just the same thing as 9 and 2.
Mm-hmm.
Except with different lists. So
yeah,
that's how the algorithm works to get to this figure.
Okay, that's I think enough for now. And Miguel, do you have any concerns or questions about this portion?
Yeah, very good.
Okay, good. And so then there's some intricacy about what happens after we reach figure 8, because that's when we really need to figure out how do we find all the objects that have 0 count or 0 predecessors, and then we need to start removing them, and what happens at that point. So that is now described in algorithm T on page 265, and let's spend about 7 minutes on that.
Mm-hmm.
Okay. So how do you feel about the algorithm? I think it's really the step T4 onwards that, wasn't really very clear in the diagram on the preceding page. So we can just focus on that.
What makes it even harder is that he's reusing that counter.
Yeah.
So that in the middle of the algorithm, half of it is the order of the list that you're outputting, and half of it is the counters. And he needs to. It's like he says it's overlapped, and I mean that count field. First thing is that the count field goes from 1 to 10, and the QLINK field goes from 0 to 10. That's the first thing to keep in mind. And the second thing is that in the middle of the algorithm, half of the numbers are QLINKs, which link the elements in the order that they're going to appear in the output, and half of them are still counts. And you don't know which are which.
Yeah, that's true, but that's only a concern if you have a view of the whole thing and you're looking at everything at once. But in terms of the actual processing, you're not concerned with those counts because they were.
That's true. That's true. He called it thank God he called it QLINK when he's talking about the link and count. He could have just called it all count.
Yeah, he could have.
Then it would have been really confusing.
Yeah.
So you can, in your mind, say, QLINK is a separate array from count, which in a sense it is. But he points out at every step that, I'm calling it QLINK and I'm calling it count, but they're really the same thing. So I'm replacing one with the other. And I have to keep in mind that the tables overlap. That's what he means. Half of them are QLINKs and half of them are loads. So, or half of them are counts. So,
okay. So can you just explain?
More words, which make the algorithm a little bit more complicated, in my opinion.
I completely agree with that. The QLINK could have been a completely separate queue. It would have been a little bit more verbose, but yeah. So what happens? How does QLINK start out?
All zeros.
What do you mean by all zeros?
Well, no, it doesn't really. QLINK, the only thing that you can say is, well, I think of it as starting out as all zeros, meaning that I don't have anything. QLINK is going to be the nodes in the order that they're being output by the source. So it's the list.
So is it? I actually am confused by that yet. So count. So before getting to QLINK, so count and top are both part of the same node. Right.
Well, count is information, so count is not a pointer.
Yes, but sure.
Top is the top of your stack.
Yeah,
But Michael, I would argue that top is also information because it's just information represented as a list, but it is still data. It's not
Okay.
simply, you know, a pointer
Okay.
for the structure.
Okay, but they're different. Top is an
Yeah.
address, and info is a number.
Count is an actual literal number, and top is an address to something else.
Right.
No, the part that I'm trying to understand is, and then it says QLINK is the same. So it sounds to me that it's saying that either that they are literally the same, that they have the same offset. So trying to see in the terms of implementation. So there is a word, which is a big number, an octa, tetra, actually. It's a tetra, right? Yeah. The tetra. And then one half used to be count, and the other half was top. So now QLINK, what is QLINK then? Is it the same offset as count? It's literally the same as count? Because it's saying here that QLINK of 0 is 0 eventually, but QLINK of the first element is the same as than count, literally the same number.
Well,
They start.
QLINKs are going to be small numbers.
No, sure. But trying to picture it in terms of offsets of the word, what is being stored? So are they, the part I'm trying to understand is, are they like an extra space where we keep that count? Or are they being referred as the same actual number? I mean, when you say, you know, when we saw the code for inserting in the linked list,
yeah,
and this info was the offset. Info was 0, info was 8, and link was 0. So if you wanted the link, was linked to get the offset of 8, right? So the question here is, are QLINK and count actually the same offset?
Yeah,
So
they're the same.
It's just two names for the same data.
Two names for the same thing. That's what he's pointing out, is that they're the same, but you could just as easily make them different, and it doesn't matter whether they're different or the same. The only reason to make them the same is that you save an extra word an extra word or an extra. You said tetra, but in the MMIX supplement, everything is a word, and
right.
in the original mix, he puts that info, packs it all into one word, which you could do because you got 8 bytes there.
So I think I have like a vague intuition of what the whole thing is doing, but honestly, I think I have to reread it. Yeah, carefully.
So Miguel,
let me see if I got it. They have, by the end of the whole thing, they traverse the list again by the list of the count on top, and every time it finds a 0, it pushes that 0 into a new queue. Wait, some queue somewhere. Wait, what am I talking about?
So Miguel is right about the tetras, though, Michael. In the MMIX version, the object struct is 2 tetras. The count is a tetra, and top is also a tetra. So it's not a full-fledged address. It's sort of like an offset into.
Relative to base, they used to say, whatever base is.
Okay, but on the insert and delete that we did, info was 0 and link was 8.
That's true. So in the more general case, he used that 2-octa representation. Okay. But here in the actual MMIX code that is in the supplement,
for the topological sort.
Yeah, for the topological sort. And we'll get into that. We'll get into that when I do the demo afterwards. But so going back to what is QLINK starting out. Oh, by the way, I did want to point out that the nodes I'm not going to call them nodes. I'm going to call them objects. So the objects that have the count and the top fields, that's not actually a linked list. That's a sequentially allocated list or an array.
Could be, yeah.
I see. That's why you can say, give me the 5 straightforward.
Yes, yes. So that itself, that number of slots that corresponds to the number of objects, that's a sequential list. But one of the fields in each one of those objects, the top field, is the beginning of a linked list.
Right. Yep.
All right. That's why it says that they are relative to base, and base presumably is that you can compute it using the index that you have. So you know where the sequential list began. You have the index, so you got your base. Therefore, you have the rest of the address.
Yeah, that's absolutely right. So now you've got two directions for traversal, right? So there's the original objects, which is that sequential list. And then there's the vertical linked lists, and those are related to the base, which is some address. It's not clearly spelled out here up to this point, but there is some base address, and then the top is an offset into that base address, and then that gives you the beginning of the successors of that particular object.
So basically, you initialize QLINK 0, which doesn't link points to anything, because the QLINK that belongs to actual objects begin at 1. So QLINKs would then link to the first object we find with count 0. And as we keep scanning the list, we will put, as the part that I can still find confusing, QLINK of that index. So the QLINK of that basically is the count will now I don't understand what you're saying. It has now an address. Is that what it's? It has an index now. What is? I don't get it. So now instead of having an actual count, it has an index basically.
The ones that have zeros at the end.
Go ahead. Go ahead, Michael.
At the end of T4, the ones that have 0 for the count are now QLINKs, and QLINK of 0 points to the first 0. If in the diagram above, that would be 1, so QLINK of 0 will be 1. QLINK of 1 will be the next 0, of which it would be 9. And then QLINK of 9 is, I don't think it's set at anything.
QLINK of 9. 9 is the end. 9 is the last.
Initially, there's just those two, 1 and 9. In the first pass, we just get 2 values in the QLINK queue. 1 and 9. What happens after that? What happens in?
So what tell me if I got it right. Then it will QLINK of 9 will not be 0 anymore. Will be no wait what?
What? Okay, so actually, Miguel, that's a good question. What happens when we add something to QLINK? So obviously, QLINK and that queue changes, but something else needs to happen, right?
For each case, so you go for each of the numbers, so the sequential list. We look at count. So count of that number, count of 9, will be 0. If it's 0, then set QLINK of R. QLINK of R. R is this global. Is a rear.
Yeah, that's just saying basically insert it into the queue, and everything that gets inserted into the queue gets inserted at the rear. So that's all that's saying. And the first pass, after the first pass, we now, because initially only 1 and 9 have 0 counts. And so after that first scan, there's only 2 items in the queue, 2 values in the queue. There's 1 and there's 9. But from that point on, something needs to happen for us to proceed, with the actual sorting. And so what is that next step? What should happen with 1 and 9 in the queue?
9 and 2.
9 and 2? What do you mean 2?
What do you mean by 9 and 1?
Well, we now have a queue with 2 values in it, 1 and 9. These are the items that had 0 success.
Yeah. First pair is 9 and 2, right?
First what?
What is the first pair is 9 and 2.
Oh, well, that's done. We already processed the pair.
Oh,
The pairs have ended up populating the objects with the count and the top fields filled in, right? So we're done with the pairs.
So we are now I see. So we're now going from all the case. So you're still in the stop. So I'm still in T4, by the way.
Yeah. So T4 is basically figure 8. So we're at figure 8, and that's when T4 starts.
Yeah. So basically we start by 1. That's what you say. 1, the count is 0. So that's what you meant. So we have
we're just going through them. We're just going through each one of the objects, and any object that has count 0, we're inserting it into the queue. And you can see when we're through with the 9 objects, we will only have
inserting into the queue. That sentence, that's the part that if I had a Scala queue, I know exactly what you meant. But in terms of the actual coding and encoding in the MMIX is the part I don't get yet. What?
And I think that's very, very confusing because of the reasons that Michael had explained earlier. So if you can understand it in sort of general terms, that there is some queue and we're just adding or inserting things that have 0 count in them, then I think that's perfectly fine. For the purposes of understanding the algorithm, that's perfectly fine.
Yeah, it makes total sense. You keep putting stuff in the queue, and then you can pull them, and you know that the first you get is the first that goes.
Okay,
right?
so that's the point where we're at T5. So after we've initially we've found the first 2 items that have 0 successors. These are now in the queue. So that's where T5 comes in, and what happens from that point on.
So if there is something, tables overlap, we have QLINK equals 0. Yeah. So this is like a boundary condition, right? You're making sure that if the queue was empty to begin with, we go to T8.
All that's saying is that if the queue is empty, then you're done.
Yeah, essentially.
But if the queue is not empty, then what happens?
It puts an address, the link is transferred to P. Very back.
Michael, do you feel pretty comfortable with the algorithm?
The only thing I don't quite get, and it's only because you're overlapping, what happens to QLINK of 9 after the first pass? QLINK of 0 is going to be 1. QLINK of 1 is going to be 9. And now you've found the last 0. So what happens to that? Is it left at 0?
QLINK of 9 is now the rear.
Yeah, it's the rear,
So
but I'm not.
that's the available. That. So it's the available slot. It's the available. It's where the next 0 successor value will go. That's the rear.
We don't care what's in it. We don't care what's in it. We just have F pointing at it, so that the next time we find another, on the next cycle, we're going to reduce the counts and we're going to find more zeros, and that's where we're going to continue on.
Right. R pointing at it, not F.
R pointing at it. Yeah. Okay. Fine.
Yeah. Yeah. So from this point on, T5 onwards, we now have to start processing these objects that we have found with 0 successors, which essentially means, because it's a queue, it means start popping the queue from the front. And what happens when you get an item off the queue? When you remove it from the queue, what needs to happen? Like the front of the queue right now is 1. What should happen to that node, essentially, or what should happen to the queue and what should happen to the rest of the objects?
You're gonna go through that list and you're gonna decrement the counts of the items that are in that list. So that first list has only 1 item in it, and it is 3. So you're gonna go to count of 3 and decrement it by 1.
Yeah. Yeah.
So that'll be one of the zeros for your next pass. And then you have 9. 9 has 2 elements in it, so you're going to go to 5 and 2, and you're going to decrement those counts. 5 and 2. 5 goes to 1, and 2 goes to 0. So now you have 2 more zeros for the next pass.
Yeah.
Okay, but Michael, there's a little subtlety here. When you decrement, do you really need to wait to do another pass?
As a matter of fact, you don't want to wait. You actually want to put that immediately into the QLINK, because the next pass, I guess, isn't going to be a scan through all the items and find them.
There is no T4, right? T4 is gone forever.
Well,
yeah. So I literally scanned for it. I did. So the thing is that you do the first pass, that you scan for zeros, and after that there is no more scanning. As you go to the adjacents, then you first adjacent. How are you? Do you have, what is your count? After I decrease it 1 because I just delete your data. If it got to 0, then you go into the queue.
Right. Exactly.
5 to 5.
Exactly, and that's where I was a little bit confused when I said what happens to the count of 9 after the first pass. It's still 0, but that doesn't matter. I mean, it's still 0. We don't care about it at that point. We have R pointing at that, so that's the next 0 we find is going to go into that position.
Yeah.
But we haven't found that yet, and it doesn't matter.
And we're
not going to scan for zeros again. And by the way, one kind of cool thing about this is that after the first pass, when we found 1
and 9,
we set those zeros to non-zero values, except for the last one. So if we did scan for zeros again, it would almost work, except for 9. But it doesn't matter because we're not going to scan for zeros again. What's going to happen is after we've got that last 0 in, we go through the lists of the things that are in our output list now, which is 1 and 9
in the queue.
In the queue, yeah, okay, yeah, call it that's a better word. The things that are in the queue. The first element in the queue is the 3, so we're going to decrement the count of 3, and also we're going to since 3 goes to 0, we're going to put 3 onto the end of the queue. And we're going to decrement the count of the other item is we're gonna go to the list of 9, and we're gonna decrement 5 and 2. 5 doesn't decrement to 5; just decrements from 2 to 1, so we don't do anything with that. But 2 decrements from 1 to 0, so the next item in the queue is 2.
Very nice. Yeah.
And we keep going that way. So now when we keep going, the next item that we read from the queue after 9 is going to be the 3. Is that right? Yeah, the 3.
What do you think, Miguel?
Yeah, no, I think I got the general idea. Obviously, we need to reread it a little bit and look at the code as well. But yeah, I think it's pretty interesting how to do this like initializations just to avoid to do more work later on. I remember when I started reading this, it was like, what are you doing this? What is this counter thing? What do I care about the, how many ancestors you have? Gives a shit. And then, yeah, that was exactly what we needed in order to save work, to avoid work.
Yeah, I found that very cool as well, that we're not maintaining a predecessor list, we're just maintaining a predecessor count, and then we have a successors list, but the successors list are only used when they're really needed. Like when we start popping things off the queue, that's when we need the successor list, and we keep decrementing and pushing things into the queue. So it's really like just there's that initial scan, but after that it's almost like one pass for everything else.
By the way, I haven't successfully written any code in MMIX yet.
Okay.
I mean, I have load code from the GitHub repo and I have run, that's fine, but I haven't like start typing and things work.
You say this like it's a bad thing.
Yeah.
This program T seems to be reasonably full.
Yeah. Yeah, I think it's a pretty real program, and it's, it solves a real problem, and it's a full-fledged, input, output, and he has a lot of the tricks that I think we'll be seeing quite a bit in this. Not just tricks, but also some conventions, like in terms of the base address and the offset, and working with the registers and the naming conventions. So, yeah, so I mean, I am now going to record the demo with the actual program in the Visual Debugger. So it would be great if you guys can stick around, and if you have any questions, just like the normal thing, I'll explain things, what I'm doing in the program, and if you have any comments or any questions, I mean, that's just part of the discussion. But if you have to go, I completely understand, so that's perfectly fine. But this my guess is it'll take about half an hour or so. Just depends on how easy we find this.
Yeah, at the very least, I'm going to be the first few minutes just to see how I will start doing it, and I eventually want to get doing myself. And then I get stuck, and I can see the video to see why I got stuck.
Yeah, that's absolutely the intent. Okay, so yeah, let me switch the sharing.
So first question.
Yeah, go ahead.
Does it make a difference to use tabs or numbers of spaces between thin, is, tree, and this kind of, and general? So that
I personally don't use tabs, but I don't think it makes a difference.
okay.
It's just white space, yeah. So there's no specific purpose for white space. I can get this. Is that font good enough? Okay. All right. So this is the code from the MMIX Supplement. Essentially, it's sort of a combination from the website. Remember that German university website has the supplement code as well, but it's the problem with that website, or the difficulty with the code on the website, is that it has some markup in there, like LaTeX or something else. I'm not sure what that markup is, so it's kind of difficult to understand the comments. So I've cleaned that up, and I've also annotated it myself, added some more comments and changed the formatting a little bit to make it a little easier to understand. But essentially it is the same thing. Now, the way this works is, here's the, let's see. Here's the subroutine, tsort. So that's essentially the algorithm or the program T in the supplement. But to act, yeah, go ahead.
No, sorry. I did realize I wasn't muted.
Okay. But to actually run the program, you need a main. And so that's over here down below. Very simple main. It simply calls tsort, and tsort doesn't actually take any arguments or parameters, so we don't have to pass it any values. What tsort returns is the number of nodes or the number of values or objects it was not able to sort in topological sort order, which means that there's a cycle. So if it returns 0, that means, yeah, you can do this topological sort and it's got the answer, and if it's not 0, then there's a cycle. Okay, so let's go back to the beginning. And so what you'll see here is the directives for the assembler, the first 50 or 60 lines. The prefix, this is like a namespacing feature in MMIX. It allows you to have the same names for functions, for example, but with different prefixes. And in this case, he's using this prefix tsort. This is like some formality. It doesn't really affect anything in the program. Okay. This greg, if you remember, this is one of the global registers. Every time you say greg, it takes one of the high numbered registers and it turns it into a global register. Remember that there are 256 registers in MMIX. So they go from 0 to 255. Register 255 is always global, so you don't have to do anything with that. Global just means that it's available in all contexts. So no matter what subroutine you're in, a global register is always available as that register with that value, whatever it has. It's not hidden in any way. So whenever you say greg, the register number goes down by 1, starting from 255, and the register becomes global. Okay, so this first greg means this is register 254, or $254 as the notation goes. Now, this is a very interesting feature of MMIX, and it allows you to use very convenient addressing if you use the global registers. Once you've got a global register, like I have on line 20, then it gets the current memory address as its value. Okay, so whatever the address is at this point, that address is stored in register 254. The address is determined in many ways, but one way to do it is with the location or the lock directive. That just sets the address. And the data segment is one of those addresses that I told you about, that is an area of memory where programs are allowed to write. And it has this address that I've got as a comment on line 19. That's the address of the data segment. So on line 16, with that lock directive, I'm setting the address to that address. On line 20, with the greg, that address gets stored in register 254. Okay, once that address is stored in a global register, the assembler now knows that there's a register 254 that had this address. And then if you have any names after this greg, you can now start using those names in your assembly instructions, because the assembler knows what that address, what the base address is, and it can calculate the offsets from that base address to that name. So for example, the first name that I have here is this in name. These are parameters for input files and output files. And you see over here, in name has been allocated a byte, a 0 byte. Actually, it's been allocated two 0 bytes. There's the first one, and then there's the second one right after that. So in my assembly, I can start using in name, and I can add things to it, and I can use it in expressions for addresses, because greg, register 254, has the base address. So the assembler knows how to compute an address that has an expression using in name. Okay, Miguel dropped out, that's fine. In the next few directives, there's some more parameters that are being set for input and output. We are not really going to rely on the input and output. I've just hard-coded some data into the program for us to see, but the program does work with input and output if you wanted to use it with files. This size is a constant, and it's the size of the buffer that's going to be used to read in the input. Remember, the input is a set of pairs of numbers from 1 to n, and it's a very specific format. The format is that it's basically like this. This is the hard-coded data. So we won't be getting the input data from a file. We're just hard-coding it. And in this case, you've got these pairs. The first pair is special. The first pair will always have the left of the pair 0, and the right of the pair will be the number of objects. So in our example, we had the objects going from 1 through 9. So there are 9 objects. So this second piece of the pair, or the right piece as Knut calls it, this is a 9. So that tells me there's going to be 9 objects involved in these relationships. After the first pair, then you have all of the relation pairs. So you've got the 9 and 2, which means that 9 is the predecessor, 2 is the successor. And then you've got 3 and 7, which is 3 is the predecessor and 7 is the successor. So on. The last pair is also special. It is going to be the pair 0, 0. So that's how we know that the input is complete with this with the special pair. Okay. I've got another hard-coded data, input data over here. You can uncomment that out and try it out if you wanted to. But this one that I'm using is present as a comment here, and it corresponds to this sorted, topologically sorted order. 9, 1, 2, 3, 7, 4, 5, 8, 6, and then 0 is the output terminator. So that is saying that that's the end of the topologically sorted list. So we would expect this output in memory somewhere that we can then write out as the answer. Okay, so the buffer that holds this has this capacity, 256 times 2 times 4. So that's saying it's 256 objects is sort of the maximum that we can work with. And because each pair is going to occupy 2 tetras for the count and the top fields, and each tetra is 4 bytes. So the total number of bytes is this, 256 times 2 times 4. And that comes to 2 raised to the 11 bytes, or 2048 bytes. And in hex, it's this, hex 800. And we'll see this 800 in the debugger, so that's why I wrote it out. So since the buffer capacity is size, what I need to do is to reserve the memory region that corresponds to that size. So, it's not used for anything else. And the way I'm doing that is with this location directive that basically says that memory is now at a point, size bytes from buffer. And so anything after this point will only occur or will be placed in memory after the buffer. So what's happening after the buffer? There's another greg, which will allow you to use these following names in the assembly, in address expressions. Okay, so this greg will be filled, which will be register 253. This is going to have the current address, which you can see the buffer started at hex 28 in the data segment, and when you add hex 800 bytes to that, you get hex 828. So that's this address. So that is now the value that's going to be stored in register 253. Now, what's important about using greg's is that, or at least using them as base addresses this way, is that these greg's need to stay exactly the way they are. They can't change during the program because they're going to be used for the address computations. But there's a whole bunch of registers, so it's not a big deal. So I really like this feature. I think that this is a really nice feature in MMIX. Okay, so what follows the buffer? There is a special octa, a 0 octa that's a marker for one past the end of the buffer, right? So this is a way that we can detect the end of input or end of the buffer without actually keeping track of the size if we wanted to. There's some other input-output arguments here. We won't be using it in this demo, but if you were getting data from a file or writing to a file, then these would be needed. Then there is this base octa. So this is the sort of the end of the pre-allocated memory that we're going to use, which is essentially the buffer that we are using for the input. From this point on, the memory that is going to be used is dynamically determined, right? So it'll depend on how many objects we have, and then we'll need it for the queue, not for the queue, but for the successor lists that we have for each object, for the linked list. Okay, so there are 3 lists involved in this program. And there's the first list, which is really an array of the objects. And it has 2 fields. There's the count and there's the top. And uppercase because these are field names, these are small values. And each field is 4 bytes. So that's why count is 0 and top is 4. Okay, because count is 4 bytes, so the offset for top is 4. Then we have the linked list of successor objects, and in those, successor nodes. In the successor nodes, there are 2 fields as well. So there is the successor object value, and the offset of that, its offset is 0, and then the next pointer to the next node in the successor list. Then the third list, which is sort of this overlay on top of the objects array, it reuses the count field, but the name of the field is QLINK. Okay, then we have some variables.
It looks like I have to go. Sorry, okay. I got an appointment at 5, so.
Thanks for staying as long as you did. It definitely makes a difference, but I'm gonna press on, and hopefully you'll catch me recording.
If you record it, I'll watch it on YouTube. Thanks. Yeah. Thanks.
Okay.
For time.
Thanks, Michael. See you.
All right.
Okay, so we are going to continue with the variables, and we've got, and these are now registers. So we've got a register for the count of the objects that is in the input, and that's going to be $0. So register 0 holds that. We've got a register for the available list or the available pool, and this register will have the offset of the next available node. We've got some more registers for each of the fields in the various objects and nodes, and you can see that there's this aliasing feature. So when you use the is directive, it doesn't have to be a literal value that you give. It can be another name if you are just interested in creating an alias for that name. So here, SUC or the successor register is the same register that we're using for count. And the reason why you can do this is because when we are going to need the successor, when we're going to process the successor list, at that point, we won't need the count value anymore. So we can just use that same register. That's the way he's got it set up. And similarly, for QLINK, he's using the same register again. So remember, these are just registers, so they're just, they're going to hold certain values, and depending on your algorithm, you may know that you're never going to use a certain register, so you're always going to use a register in a very specific context, and then there's some other context in which you don't need that register anymore, so you can just reuse it for some different variable. Then there's some counter registers for different loops that the program has. There are other registers that actually hold full-fledged addresses. So then you don't need like a lot of computation. So the left register $7 has the address of the left tetra of the pair. So the pairs are, for example, 9, 2, and then 9 would be in the register that is left, and 2 would be in the register that is right? So the addresses are just going to be computed so that you can directly get the left and the right for each pair. Okay, yeah, so there's some more registers over here. I won't go through all of them, but they'll come up. All right, so when the subroutine starts, and again, we're not using the input and output files, so this is really unused, although it will work. But for the demo, we don't need to be concerned with it. So initially, what we're doing is we're just setting some initial values in some of these registers. So the size register, line 154, this gets the value of the size constant, which you remember is the buffer capacity, the input buffer capacity. The same thing here. So this is a little tricky. What's happening here is that we've got the input buffer, and so buffer plus size, this piece over here. So buffer plus size is going to be just past the end of the buffer, right? And that is this is an address. Buffer plus size is an address, because buffer was an address and size is some, offset. That address is now loaded into the left register, and left is supposed to point to the left, to the left of the input pair, right? So the way he's done this is because he wants to use negative indexing. So if you've got like a memory region, right? So let's say that this is the beginning and this is the end, and you've got something pointing, at the end. So with negative indexing, what you can do is you can subtract the entire capacity from this location, from this address, and get back to the beginning. And then if you subtracted a certain amount and you start incrementing it, then you can move up until you hit this point, which is when you will be subtracting 0. So that's the reason that I think he does this, is that he wants to test for 0 as the end of the processing of the input buffer, right? So he's fixing an address at the end. He's subtracting sort of the maximum size to start at the beginning. He's incrementing as he goes on, and either we reach the number of objects that are in the buffer, so you would terminate early on, or you reach the end, which is when the offset is 0. Okay, so that's what's happening here. We negate size and we initialize the counter I to that. Okay, if you notice in the comment for this particular line, it says I is initialized to 0 because it corresponds to, and this is from the text, by the way. So because it corresponds to the initialization of that loop. But this is an implementation difference. So the way it's implemented, I is not actually 0, but the way it works is exactly the same. So this is a little bit of trickiness, and I think we will be seeing a lot of this actually. So you just have to remember that, often the implementation will do things slightly differently, but it will behave exactly the same way as the algorithm. Okay, so since that's the case, that we have the left and the right pointers set over here, right? What we can do now is that every time we have an index or an offset I, we can just add it to left or right to get that object, to get the left or right of that pair that we're processing, right? If it's the first pair, I is 1. If it's the second pair, I is 2. And we just use I as an offset to left or right. So left and right are not going to change. And as I changes, we just end up at different pairs. Okay, so this instruction is a load tetra. So this is essentially getting the value from memory of that first pair, and then it's putting it into register n. Remember that the first pair is special. In the first pair, the left has to be 0, that's the format, and the right is the number of objects. So, if you're dealing with items from 1 to 9, that means that n is going to be 9, and so in that first pair, right is 9. So we should be able to see that. And then we're just going through the input pair. So we increment I, we increment it by 8 because each pair is a tetra. Each pair is 2 tetras, right? So in memory, we're inputting, or we're reading 2 tetras as one pair. So to go to the next pair, we have to increment by 8. So that's the comment here. I is incremented to I plus 1, but again, remember that I started out as minus size, so it's just it's now minus size plus 8, right? Okay, so that is the initialization, and then there's some initialization of the available list. This is also a little tricky. It's simplified because he says that we don't actually need to delete, and this in other words, we don't need to actually reclaim any memory that's going to happen from a deletion. So it's in this case the available list or the avail register actually just holds an offset. So it doesn't hold addresses, and they're offsets to that part of memory that was after the buffer. So it's some part of memory after the end of the buffer. And you'll see where it comes up. It's basically going to use this base as one starting point. It's actually even further out after base, but we'll see where the memory actually comes from. Okay, so what else is going on here? We've got the initialization of all of the counts to 0, which happens here. And so there's a little loop over here. You can see that there is a branch on line 195, which is referring to this name or label 1B. And 1B, if you remember, is a local label, I think, and it refers to a label that is named 1H, but in a backward direction. So the closest label that has the name 1H, that's above this statement. So if you go back, you can see that the closest label is this, 1H. So 1H means one here. That means local label or local symbol 1 is defined at this point, line 189. And so 1B is referring to this. So the branch is back here. So this is the loop here, these 4 lines. 3 lines actually. So STCO is a store constant. So this is useful for writing to memory if you've got a small value that you want to write. So then you don't need to load something into a register and then write it to memory. You can just directly use store constant. In this case, it's going to write a 0 or store a 0 into this location, which is essentially the address in count plus the offset in register K. And K is our counter register. So yeah, so this is the initialization of all of the counts and all of the top fields to 0. Once this is done, then let me just turn on the light. Okay, so once this is done, then what happens? We start processing the input. And the input, if you remember, is in the buffer. And we've already got the left and the right registers pointing to the parts of the pair. And if you have the right offset, you can go through all of those pairs. Yeah, so this piece over here is just processing the input pairs. And if you remember from the algorithm, processing the input pairs means we have to update the count fields for each object, right? As we come across each pair has a predecessor, each pair has a successor. And so for the successor, we have to update its count by 1. And then for the predecessor, we have to add the successor to the successor list for the predecessor. So those are the two pieces that need to be done. And then yeah, so there's some other implementation details. Once the input is processed and we have, I guess, the equivalent of figure 8 from the text, where you have the objects in the array, and then you have the top fields for each of the objects pointing to the successor list. That's when you can now start the sorting. And the sorting, the topological sorting that begins, there's the queue that we are using to basically get the objects in the right order, right? So as we find objects with 0 successor counts, whose successor counts are 0, sorry, not successor counts, but whose predecessor counts are 0, we keep inserting them into the queue, which means inserting them at the rear of the queue. And we keep popping the front of the queue. And as we get things off the queue, we look at that object's successor lists, and we update each successor in that list. We decrement its count. And if any of the counts turn to be 0, then we also add them to the queue, to the rear of the queue or the back of the queue. So that's essentially the algorithm. Whenever we pop something off the queue, that means it's already in correct topological sorted order. It's going to be written to memory, and that'll be it for this demo. But the final step would be that you've got the topological sorted list in memory, and you need to output it to a file. All right, so that essentially summarizes, I think, most of the code. I've again annotated pretty much all of the code, but there are some pieces over here. I haven't had a chance to annotate them, but I'll explain what's going on. However, the comments from the original program are there already. So these double backslash comments are my sort of additional explanations, and these line number comments, these are straight from the MMIX supplement. So you should be able to match them up. And yeah, okay, so now let's run through this program. And if you remember, what happens is that there's these, debugger options. So here, right? So under the MMIX menu, you've got debug, step instruction, etc. And there's also this toolbar, which I tend to use. It's really convenient. So this one is the debug / continue button. So this will start the program and it'll break at main because it's running in debug mode. So you can also just choose run from the MMIX menu and that'll just run through the program. But we will use the debug button. So I'm going to click this and then these windows appear. And I've explained them before in some of the earlier demos, but I'll just quickly run through them. This window with the black background, this is called the trace window or the trace panel, and it gives a summary of what has happened so far. Like with every instruction, it'll show which registers have changed, and there's some other details in there. Also, if there's any output, it would show up in this trace window. We won't have any output showing up, so we don't really need this, and anything else in terms of the state of the program changing, we'll be able to see in the other panels. So I'm going to close this. The way you close a panel is by double-clicking on this X in the top left over here. So remember to double-click because a single click is not going to close it. So double-click, that goes away. And let's see what else. Up here, top right panel, these are the registers. It'll only show the registers that have been used so far. And whenever a register gets used, sorry, not used, but changes, it gets highlighted in red. But so far, there's only two local registers, 0 and 1 in use. Down here, this is the global registers. And if you remember, 255 is always global, so that's always going to be here. And our program has two greg directives, so there were two new global registers that were designated. And so the first one was 254, the second one was 253. So that's why you see three registers here. Down here, you have the special registers. They won't concern us, so I'm going to close this. And okay. Down here we have memory panels. So these are the three panels that show up automatically, corresponding to the beginnings of the three important segments. So there's a couple more segments, and you can see those panels as well if you wanted to. It's down here. You've got the text segment, data segment, pool segment, stack, and negative. Negative segment is for the operating system, which it doesn't exist right now. Okay, so address 0, that's the text segment, which is the code. We're not concerned with that because we don't need to understand the instructions. So I'm going to, actually, I'm not going to close these panels. What I'm going to do is I'm going to change the address that these panels are showing because there's certain other parts of memory that we're interested in. So I'll leave these panels open, but I'm going to change the addresses. This address is the data segment, and you can see over here the data that we filled in, right? The fake input data. And we know that our data is tetras, so I'm going to change this later, not right now. This address is the, this is called the pool segment, I think. Let's see, memory, yeah, the pool segment. So the pool segment is like the heap that we are more familiar with in terms of terminology. But yeah, so this is dynamically allocated memory that the program can use. And yeah, so what are the addresses that I'm interested in? I'm interested in the addresses for our stuff. So for example, I am interested in the buffer, right? Because the buffer holds the input pairs. And so I'm going to use this address, which is 28 bytes, hex 28 bytes into the data segment. So I'm going to copy this and put it into the first panel, okay? And I'm going to change the starting address of this to hex 28 bytes. So then we should be seeing the buffer. And let me make this a little bigger. Okay, so you can see over here, this is highlighted in red because this is the start of the program, and these are parts of the memory that have changed up to this point. So what are we seeing in memory? We've got the tetra format clicked, so memory is being shown in chunks of 4 bytes. And you can see that the first tetra is 0, second is 9, then third is 9, then 2, then 3, then 7. This is exactly what we have here. So that's the directive that we use to set, some portion of memory to some value, and we set them to tetras. So that's what it is. And so that's the input buffer. So what else? Then the other thing that we are interested in is base, because this address is where all of the memory that we're going to use for the object array, and then for the successor lists, that's going to come from memory that's after base. So I'm going to use this address down here in the second panel, which is 840 x. Okay, so that gives me base. And what else do I need? Yeah, so then there's another piece of memory or area of memory that we're interested in. After we allocate the objects array, which is a sequential list, right? From that point on, memory is going to be used for the pool, the storage pool for the linked list. And since I have 9 objects in my input data for this particular run, right? So that'll depend on how many objects we have, but we have 9. So if you remember in figure 8, you can see that each object takes 1 octabyte or 2 tetras. And so I've actually computed over here, what does that mean for 9 octas in this comment. So I'm going to use this address in the third panel. And this will let me see the memory that's being used for the successor list. So those are the 3 areas that we're interested in. We're interested in the input buffer, because that's where the pairs are going to be read into, and that's already done because that is hard-coded into the program as data. Then we're interested in the objects array, which is going to show up in this middle panel. There should be 9 of those. And those are those are also tetras. So let me change this to tetras. Okay. And then we are interested in the successor list. So those are also tetras, I think. So let me change this to tetras as well. All right, so now let's start stepping through. And this is the button for stepping right next to the debug button. And click that once. We were at main. The program broke at main when I started it in debug mode, and now after one instruction it called the subroutine tsort. So now it's at the beginning of tsort. Over here you can see the red arrow, and up here you can see the register stack. No parameters were passed, so there aren't any registers that are interesting to us right now, but the dash, this is the whole, which is in sort of the calling convention. It's a detail in the calling convention, like what happens to registers when a piece of code calls a subroutine. So some registers are hidden, and there's one register that's the whole that is sort of like, it's hidden, but its value is not available later when we go back. But anyway, these are like subroutine details. We don't need to be concerned with them right now. But you can also look at some earlier videos or demos where I do explain this. There's also a program called subroutine.mms in the same samples repository on GitHub, and it has a very thorough example where you can see what happens when a subroutine is called with all the registers, and there's a lot of comments in there, so you can have a look at that. But again, it's not something that is necessarily useful for understanding these algorithms. Okay, so let's see here what we have. We're at the beginning of this. All right, so initially we are going to open the input file. We're going to read the input file. We're not using an input file, so that doesn't concern us. We'll just step through these instructions. Nothing should happen. And then this is stuff that I'd explained earlier. We're just initializing some of these registers to certain values. The size register holds the buffer size. So you can see that the size register, which is register 14, got this value in there, 800, which is hex 800, and that's the, if you remember, that's the size of our buffer, right? And then we are loading the address of the left half of the pair in the buffer into the left register. Okay, so this is again past the end of the buffer, because remember we're using negative indexing. So we're going to set a base that is just beyond the end of the buffer, and then we're going to use an offset that brings us to the beginning of the buffer, to the first pair, and then we're going to increment that offset and move towards either the last object or the end of the buffer. So yeah, so then you have the same thing with the add with the right half of the pair, and that's simply the left half plus 4, right? Because each value in the pair is a tetra. So that's that computation, left plus 4, that gets stored into right. Okay. Then we've got, what do we have here? We have, we're initializing this counter I to loop through the pairs in the buffer. And for that, this is again, it's using this negative indexing because we're setting the base to be the end of the buffer. So we do that, and we read the first pair. Okay, so the first pair is special. The left half of the pair is going to be 0. It's down here, right? So this piece of memory, this is 0. The right half of the pair, which is this piece of memory, is the number of objects, so that's 9, and you can see $0, which is the register whose name is N, right? That got set to 9, and so now you have N is 9, so that we know the number of objects we're dealing with. Okay, and we increment I by 8 to get to the next pair. Now we want to start reading the relations. And okay, so let's step through this. So this is still just initialization. This is just getting some initial values, setting things up. It's setting up, initializing the avail, the available list. So if you remember the objects list, which is a sequential list, that's an array. We now know, since we know the number of objects that's involved, we now know how many objects we will need in that array. So that's going to be, n objects. Each one of them is going to be 8 bytes, and we allocate 1 extra object because we're going to reuse the count field for the Q. So there is an extra object. So there's a total of 10 in this case. The available list needs to start past that, right? So we've got the array of the objects, and then the storage pool that we're going to use for parts of memory for the successor list. That's what the avail register will need to give us. That needs to start after that array, right? So that's why avail is being initialized to now that part of memory past this array or sequential block of memory that we know we will need for this many objects. So that's done. Then we initialize these two address registers to the count and the top fields. And this is, the array starts at base, and so the first object corresponds to sort of this index 0, which is not a true object, right? Because it's our objects actually are numbered from 1 through 9. So the 0 is sort of the special object that is needed for the queue, and just the general operation of the links. And Okay, so what is happening here? This piece is we're going to initialize all of the count fields and all of the top fields to 0. And the way it's done is through this loop that goes from these 3 instructions. So I had kind of explained this earlier when we were just going through the code. And so now we are going to see the we're going to see what happens when we step through this. So what is going on here? We've got this instruction, that's a store constant 0, and it sets an octabyte, right? And we're just using this for convenience, since we know that one object occupies 1 octabyte, even though it has 2 fields, count and top. Both of them need to be set to 0, so we're just doing it using a single instruction, right? So instead of setting a tetra to 0 and then setting another tetra to 0, it just stores a constant 0 to set both tetras to 0. So this should run 9 times. I'll just step through it quickly. And so that's, I think, 1. You know, it just keeps on doing that. And because we're initializing things to 0, we're not going to see anything change in memory down here. Nothing will get highlighted because everything is 0 to begin with. So we don't get any visual indication of what's happening in memory, but you know, zeros are being written, they're just not being shown. So at some point this loop will stop, and so at this point we just drop out of the loop and we start to process the input pairs. And the way this happens is, again, a little tricky. It's sort of this assembly language way of doing things. What's going to happen is that there's a loop here for the entire processing of the input pairs. So it starts at this label T3, and then it kind of goes down to over here to line 234, where there's a branch to T3. You can see that here. Okay, so that's a whole bunch of lines, and what's going on here is that there's a piece of this loop, this piece, where there's an update that's happening just before the branch. The left and the right values are processed of the pair, and then the index is incremented. So back up here, when we enter the loop for the first iteration, what's happening is we're not entering it through here, through line 202. We're entering it in the middle of this code block, up here or down here, and then we're proceeding. So that's what you're going to see. So we are going to jump from line 198 to line 227. We're going to sequentially go through these instructions, 1, 2, 3. Here we're going to to branch or jump to T3, which is the beginning of the loop up here. So that's what's going to happen. All right, so let's do that. Step, now we're at T2. We process the next pair. Remember, we've already processed the first pair, which was special, which had the number of objects. So in the second pair, which is down here, the second pair, which is really the first relation pair, it's 9, 2. So the left is 9 and the right is 2. And that's what happened. In the register for J, which was register 5, we placed a 9. And then in the register for right, we're going to place a 2. And so that's register 6, you can see over here, register 6. Okay, so then we have that, and this is, what else will it do? It will also do a couple more things. So let's see that happen by stepping through. So we step, and then we branch, and we're going to obviously branch because we're not done with the input yet. And so we go back to the top of the loop, and so K is the successor that has the value of the right of the pair, right? So that was down here. You can see that register K was set to right. Okay, so when we're back here, K now has the right, which is the successor, and we're just scaling it to octabytes. So we multiply it by 8, right? Shift left is a shift left of 3 bits, so that's multiplication by 8, and that gives us the offset of the successor object, because for every pair we have to do these two things. We have to increment the count field of the predecessor object, and we have to we have to increment the count of the successor object because it has a predecessor now. So the successor object count field is incremented, predecessor object, the successor list is updated. Okay, so the first thing is going to happen with the successor object, which means that the count field needs to be updated. So that's what's happening in these instructions, lines 205 through 207. There's a load where we get the current count for the successor object, we add 1 to it, and then we store that tetra back to the memory location, right? So where are these successor lists? So these should be down here in this third panel. If I've got the addresses right, we should see a 1 show up here because we're going to increment the count for one of these successor objects. So let's step through. Okay, so that's register 15 got incremented, and then so it's actually over here in this middle panel. Let's see, this was the input buffer, and this is oh yeah, because this is the count field. This is the count field which is actually in the objects array. So this is not in the successor list so far. So that's why I think my addresses are correct. This is, and so which tetra is this? So K was 2, right? Because the first relation is 9 and 2 down here. So the first successor that we came across was 2. So what that means is that in our objects array, we remember that the first object is the 0 object that it doesn't represent, any of the objects in the relations. The objects start from 1. So then the object 1 is this pair of tetras, object 2 is this pair of tetras, and the first tetra is the count. So that matches up, right? So we've got a 1 in this first tetra for object 2. So that's good. And now we need to add k, which is a successor, to the successor list of the predecessor. And because that's the linked list structure. This whole section is about linked lists, so that's where the available storage pool or the avail list comes into play. So now the first thing we need to do is to get a node from avail, and this is a very simplified avail because of this particular algorithm, and it essentially just is going to give whatever that first memory location was that we initialized avail with. It's going to give that to P. P will become our new node, and our nodes, remember, have 2 fields. There is the successor field, which is the value of the successor, and then there is the next field, which is the link to the next successor node. And so over here, P is the new node, so let's step through that. And yeah, so you can see that the register P, which is this register 9, it seems, it gets an offset. So remember that this is a simplified avail list scheme in which avail doesn't give you an address, it just gives you an offset because we're using some base address and we can just add the offset to that. So and then on line 214 we're updating the avail list, right? Because now we've given away one node. Avail needs to now point to the next available node, which was essentially just the next octa in memory. So again, it's a very simple scheme. You don't need any links in the available list itself. It's just sequential allocation that is sort of this pretend linked allocation. But yeah, so avail gets updated, and then we now start using the new node. First, we store the successor value in the successor field of the new node, which is going to be this suc register added to the P offset. Okay, and we step over this, and you see over here, down here, the third panel, the bottommost panel, this is where the avail nodes are coming from, right? And so the first one was this. The first node that we got was this. And this becomes the first node in the successor list for 9, right? And we haven't set that yet, but we know that that's going to happen because the first pair that we're processing is 9, 2. And so that's what's going to happen next, is we need to we need to take this node and we need to essentially insert it into the successor list of 9. Remember, this is the very first successor node that we're working with, and so all lists are empty right now. All the top fields of every object are empty. And so this is the first one that's going to be inserted here, and you can see the couple of steps needed to do that. The top of the current object is loaded into this temporary register T, and we then use that address, which is now in register T, and we store yeah, okay, so there's two things happening here. We need to store the new node, or sorry, not store, but we need to set the top of the top for the predecessor object. That has to be set to the new node, right? And then top needs to be updated. Sorry, top the new node. Okay, just a second here. We've got top of J. Below that, we set the next of the new object, of the new node, to the top. Yeah, that's right. It just so happens that top is empty right now. But let's say that there was something already in the successor list. So this is operating like a stack. So we're going to take the whatever the current top is, and we want to set the next of the new node to the current top, and then we want to set top to the new node, and that will make the new node the top of the successor. So that's what's happening in these two stores on line 222 and then line 224. Okay, so that was one pass through the processing of the input pairs. We just processed one pair, and then we update the left and the right to the next pair. So the next pair is going to be, let's see, there was 9 and 2 down here, 3 and 7. So 3 will be the predecessor, 7 will be the successor. Same thing will happen, right? For the successor, which is 7, the count is going to be incremented, and then for the predecessor, its successor lists or the successor stack is going to be updated with a new node that has 7. Just exactly what we went through. Okay, so that I will step through again. There's a way to set breakpoints, so you can set breakpoints, and then, in fact, let me do that. I'm going to set a breakpoint over here, so which is out of the loop. So when yeah, I think that this is a good point. So you just click in the left column here, just by the line number, and then you've got a breakpoint. So then I don't have to step through each of these instructions. I can just click debug continue, and that is going to stop at the breakpoint, and it'll have processed all of the 9 no, I don't remember how many pairs I had, but yeah, whatever the input was, it'll have been processed. We will end up with a memory representation that will correspond to figure 8, right? So we should see like a whole bunch of red in this middle panel as well as in this bottom panel, with the successor lists being updated, with the counts being updated. So once we do that, we'll examine it. Okay, so let's do this. Oh, what happened? Oh no, this was a bad idea. Yeah, this was not a good breakpoint. This was a very special case where a second buffer was being filled. We had, a file that we were reading. So let me skip this. And it's actually what I wanted to do was to set a breakpoint here. Yeah. So I'll just rerun the program. But then I have to, let's see, what did we have here? 28, 840, 888. So that's what we'll need. Okay. Do this. This. Oh, okay. So it maintained my starting addresses, which is great. So I'm back to where we were. Let me just close the special registers. And you can see there's a lot more red because everything that changed up to this point is being highlighted. But here you can see that we've now got the objects array all filled in. So these are tetras, so this was the first 0 object. This is object 1. This is object 2, right? And you can see object 1. If you remember, one didn't have any predecessors, so that's why its count down here is 0. So this is one of those items that is going to be selected first for the topological sort. And this 80 is the top of its, or the offset into the top of its successor list. Okay, so that's there. This is object 2. It has 1 predecessor. Object 3 has 1 predecessor. Object 4 has 1. 5 has 2. 6 has 2. 7 has no, am I reading this right? 6 has 2, 7 has 1, 8 has 2, and 9 has 0. Yeah, so I think I'm reading that right. Okay, so these are the objects, and down here you can see these are the successor lists. So all of these blocks of memory came from the avail list, which again is a very simplified scheme. But yeah, so that's the initial sort of pre-processing phase. Now we actually start the sorting. So what happens in the sorting? What happens is that we have a first scan of the entire objects array. We are looking for objects that have count 0. These are objects that have no predecessors. So since there's no predecessors, that means that they are the first objects that should be written out in topological linear order. And how do we make sure that they're the first? What we do is we maintain a queue. So that's all in the algorithm. But in the implementation, the queue, and actually in the algorithm itself, the queue is overlaid. It's sort of a virtual queue. I shouldn't say virtual, but it's a queue that's making use of an existing structure, and that existing structure is the objects array itself. This middle panel, remember, this is the objects array. And in the objects array, the first tetra of each object is the count field. Now, once a count is 0, or when a count is 0, and we've processed it, we no longer need to know that count, because we're just going to, that's all that it's needed for, is to determine that this object had no predecessors. And once we've done the right thing with this object, then the count is useless. We don't need it anymore. So that's the idea behind Knut's algorithm, where he's overlaid the queue. He's constructing a queue using pieces of memory that are being left behind. So it's sort of this queue that is reclaiming parts of memory or fields in these objects that are no longer needed. So the first time we'll have two objects that have 0 predecessor counts. And since that's the case, we do get 2 of these fields reused, and it is object 2 and object 9, right? Those are, let me tell Michael that he is still on video. I don't know if he will see this. I don't know if he realizes this. All right, well, hopefully we won't be intruding on anything, but yeah, so that's the case. We have this queue now that we need to fill, and there's this initial scan. We'll just go through all of the objects. Whichever objects have a 0 predecessor count, we're just going to add them to the queue. And as I said, this queue is going to be constructed out of the count fields of the objects that we've determined have no predecessors. All right, so let's do that. And this R register is the rear of the queue. So that's what it stands for. And similarly, there's an F register for the front of the queue when we need to pop things off the queue. So this is the first pass. Right, we examine the count here. If it is 0, let's see. I'm just wondering why I'm not seeing any red down here in the QLINK. Predecessor count. Okay, so there I just saw one red. Oh yeah, the reason, let me see. This first pass, okay, I think let's do this again. Let me set a breakpoint. Object predecessor count. Yeah, let me just keep this breakpoint here. Let's run this again. Okay, let's see what happened. Close the special registers. Step through this. Okay, so we are doing a reverse iteration over the array of objects. So we start from the end. So the first object that we process should be object 9, which had no predecessors. So we should see that reflected in some update. Okay, we check the object predecessor count. That should be 0. So T, which I believe is register 15. Since it's already 0, it doesn't get highlighted. And then, yeah, so that's what happened. It did happen. Okay, so because you see that we branch, right? PB and Z is probable branch if non-zero. So we checked the count value, which was in register T. If it were non-zero, then we would have branched to this address. But since it is 0 for object 9, we fall through, and now we're going to insert this first object into our sorted queue, right? The sort order queue. And so here we should be setting the QLINK of 0 should be set to 9, because that's the object that has no predecessor at this point. So and you see over here, this is the reused count field of object 0. Remember, it's that first object that is needed just for the queue, wasn't used for the objects array. But this is the first item in the queue. So the first item in the queue is 9. What you see over here is actually hex 48. And hex 48 it's not 9 because it's scaled. It's scaled by 8 bytes. So hex 48 is 72. And 72 is 9 times 8. So this, what's being stored is not the index 9, it's what's being stored is the byte offset into the objects array. So it's saying that, you know, the first topologically sorted object is at offset hex 48 or 72 decimal in the objects array, which is the 9th, not the 9th, but the object at index 9. It starts at 0, goes through 9. Okay, so that's the offset there. So that's good. We got the first item in the queue, and then this should keep on happening. We should keep going through the objects array, but remember that the only 2 objects in the beginning that have no predecessors are 9 and 2. So everything in the middle, they do have predecessors, so we won't see any updates being reflected. But let's just step through these things, and at some point we should see this. No, not this, but we should see the count of of object 9, which I think is this one. This one should get updated to the offset of 2, which will be 2 times 8, which is 16 decimal, or 10 hex. Okay, so let's see if that happens. Okay, so it should happen at this point, right? We didn't branch, we fell through, and so now we're going to update the queue. And yeah, so something did get updated. We got an 8 here. Why is it 8? Oh, because it's not 2. It is 2 actually. It is 2. No, wait a minute. This is the object that had no predecessors. That's 1. That was 1. There was only 9 and there was 1. Those were the only 2 that, let's go back and look at the input again. This is the input, and this is the sorted order. Yeah, so after 9, there was 1. So that is correct then. We do have the right value stored here, because object 1 scaled to octobytes is 8. So 8 is the offset of the object in this array, right? So that is correct. So the first item in the queue was 9, then 9's count field is reused for the second item, and that's it. Like the first pass, we just have 9 and we just have 1. And then we enter the next phase of the processing, which is we start to pop the queue, and for each item that we pop, we go to the successor lists of that object. We start decrementing the count of each of the successors, and any count that becomes 0 after the decrement, we add it to the queue, and we just keep doing that until the queue is empty, right? So so that's what's going to happen in the next chunk of code. Okay, so let's do that. So we've got this loop here. No, I think we're not done with this loop yet. This is still the old loop. Yeah, so now this is where we start popping. Okay, so there's some stuff about writing to an output file. In this case, we're not going to do that, and so we're not really interested in that. We'll just see it in memory. And where is it in memory that we write out the popped values? Okay, so let's see where that happens. So here, first of all, we pop off something off the queue. So QLINK 0, that's the first item on the queue. And F is a register that stands for the front of the queue. So F, oh, this is right now is just the front. Yeah, we're just initializing the front, which is fine. And then what we want to do is to go through this queue, popping the front, and then updating as we need. So it's again this negative indexing. The starting point is the end. Not sure why I've written buffer end. I don't think that we are iterating over the buffer. Are we? Or is it the or we are overriding the buffer? I think that's what it is. Yeah, I think we are going to write the sorted list back into the input buffer because we don't need the input buffer anymore. So that's what's happening here. So there's an index to allow you to just go to the next available slot in the buffer where you can write the value, and the values are tetras. Okay, so that's some initialization. We go to T5, and remember T5 is in the algorithm. That's one of the steps, T5. And this is again the same thing we saw before, where we jump into the middle of the loop for the first iteration, and then we go back and actually start looping. And so let's see what's happening here. We take the front, I guess scaled or downscaled. We are shifting right by 3, which is division by 8. And that way we get some index. And because remember, we want to actually write the value of the object. Objects are 1 through 9 in this case, but a lot of places we've scaled. Like when we were storing something into the queue, we stored the scaled offset because that would allow us to quickly go to that object and reuse its count field. But now when we actually want to write the value for output, we don't want to write the offset. We want to write the actual object value, which is, instead of 8 being the offset, we want to write 1. And similarly, so that's just the shift right over here. And so the first one, if you remember, was 9 that got inserted into the queue. And you can see that here, register 15 is now 9. So that's after the downscaling or the division by 8. And then we store, right? So as I mentioned a few minutes ago, that's an index into the input buffer, which we are reusing for the sorted list. And so this is, if you remember the first panel of memory, this is the input buffer area. And so we should see a 9 being written in this panel. So it should turn red. And so let's do that. And yeah, so the first tetra became a 9. Okay, so that is the first pass. Oh, well, we're not done because we output the front of the queue and then we have to do the processing associated with that pop, right? We have to go to the successor list of 9, all the successors, and we have to decrement the counts for each of those successors, and if any of the counts turn to 0, we have to add that object to the queue. So let's see how that happens. So we go back to the top of the loop, and there's some check here for the buffer overflowing, which we don't have to worry about. we update the number of objects that we have processed. Remember, n started out as the number of objects in our input, not the number of pairs, but the number of objects, which is 9. We've processed one of them, so we have to now decrement n by 1, because this is going to be our return value as well. So if it goes down to 0, which means that we've successfully processed all of the objects and we do have a topologically sorted list. Otherwise, if it doesn't go down to 0, that means we came across a cycle. And yeah, so let's just do that maybe for a couple of passes. And so what do we need to do now? We need to go to the top of the object, the top of the successor list of the object. Remember, the register F has the offset of the front of the Q. And so when you add it to top, that'll give you the top field. Okay, so we put that into P, and then we check if P is lambda, which means have we reached the end of the queue. This goes back to Knut's scheme explained in the section, for dealing with an empty queue. And so that's the test, and the queue is not going to be empty right now, so we won't branch. And so now what do? We load the successor value into register S, and then we go to the count field of that successor object, and we have to decrement that count. So that's what's happening in these lines. Okay, so let's do that. Decrement, and then update in memory the new count. Okay, and check after the decrement, did the count become 0? Because if the count became 0, we need to add this object to the queue. In this case, T, which is register 15, is 1 after the decrement, so this is not a candidate for the queue, and so we are going to branch because it is probable branch non-zero. And notice that it is probable because it's likely taken, right? It is likely to be taken in general because counts will take a while to get to 0, right? So more often than not, it won't be 0. So that's what happened. We went to we're updating P to the next because we're traversing the successor list, right? So the successor list, we processed one successor. We found out that its count after decrementing did not go to 0. So now we go to the next successor. We do exactly the same thing. So there's a little loop over here, this piece over here, and that's what's happening. So we follow the next pointer. We check, if there is another successor which in this case it looks like there is. So we go back to T6 and we have to now decrement the count of this other successor. This one did turn out to be 0. So it became 0, which means this successor object needs to be added to the queue. And so at this branch, right, line 307, we're not going to take the branch. We will fall through and we are going to update QLINK. Remember the way QLINK works? That's just, you know, whatever we did before, it'll happen again for, and down here you see this, that the, you know, field previously known as count and now known as QLINK, that gets updated with this new item. And remember, these are offsets, not the actual successor object. So this is hex 10, which is 16 divided by 8, so that's 2. So that means the successor object that just got inserted was 2. And is that right? This is the correct answer that we should have at the end. So that looks right. After 9 and 1, 2 is the one that gets inserted, and then it's 3, 7, and so on. Okay, so that looks good so far. Go back down here. Where are we? Okay, let's just step. Okay, there we are. So yeah, so that's what's happening. 9, remember, was the one that was the object that we were processing. That's the first item off the queue, and we have now processed its successor list. 9 had gotten written out already into memory, and at some point we should see 1 being processed, being popped off the queue, then, you know, everything happening with that. So we should see a 1 appear. Yeah, so that's what happened here. So 1 showed up in memory as the second value in the topologically sorted order. And let's just do that. And, you know, you can maybe play this in slow motion to step through this and understand, but yeah, I guess I'll just step through each one of these instructions, and we should see these pieces over here in the first memory panel getting highlighted as we write out each successive topologically sorted value, right? So now we have 9, we have 1, we have 2, we have 3 so far, 4 values. And you have this program available, you know, and you can install the Visual Debugger, and you can just run through this. You can try out other examples, but yeah. So how far are we? We're at 4, 5, 8, 6. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that should be the last one. And at some point, the queue will be empty. So I think that's it. Yeah, the queue emptied, and there's some piece of code here that writes out this piece of memory to the output file. We don't have an output file, so nothing's going to happen there. but the subroutine will return. You can see that n, which is the return value, which was $0, is actually 0, right? So that's success. That means that all of the objects were processed and written in topologically sorted order. So let's just finish that. Pop, return, and yeah. So $255 in the main program, which is the first global register, that holds the exit status of the program. So when the program exists, you know how you run a program on the command line, and there is an exit status, from which you can tell whether the program succeeded or not, and 0 means success. And so that's the way in MMIX you can set the exit status of the program, is by placing a value in register 255, and that will be shown as the program's exit status when it terminates. So yeah, so I think that's about it. I hope that's useful. Took way longer than I expected. I may try to find a way to cut this down, maybe not step through things as much. But yeah, I mean, this was kind of a simpler program, but it is you know, a useful algorithm. It's a real algorithm. But as we go through more and more algorithms, the programs are probably going to be a little more complex and longer. But yeah, so let me know in the YouTube comments or the Meetup page, you know, like what else you would like to see in terms of making these programs and the code and the algorithms understandable and accessible and usable, because the whole point of this is really not just for you to view and learn, but to also be able to use these algorithms and programs, and you know, so being able to actually use these files, run these files, make changes, write your own programs, things like that. But this was a good I think good experience for me as well. And you know, I am you know, we go through these algorithms and programs together in the Meetup, and again, you can go to the Meetup page, but anyone is welcome to join from anywhere in the world. We are very regular about meeting every Saturday, so it's you know, relatively frequent. And we do go through these things together as a group, but there's only so much time. So, you know, it's like if we did everything and it required everyone to participate and attend, then things would slow down a lot. So some of these things, I'm hoping whenever people can join, if they have the time, then they can share in this experience and contribute to the experience. But I hope to be doing more of this so that we can keep moving along and people can still have sort of both of the benefits of being able to go through TAOCP in a group, with a group, but also have the opportunity to look at things on their own when they can. So thanks for watching to the end. And again, any comments, any feedback that you have would be really appreciated in the YouTube page or on our Meetup page. And if you can join, that would be the best. Thanks. Bye-bye. Something about our next meetup, which is scheduled for next Saturday. We will be looking at circular lists, and there are algorithms for the addition and multiplication of polynomials. So that's on the agenda for next week. And if you are interested in getting these programs and anything else related to our project, it's all on GitHub. There's a Facebook page as well, and there is obviously the YouTube channel that you're watching. Okay, so finally, bye-bye.